Welcome. Thank you for coming along. My name is Jonathan Cullen. I'm joined by Andre Serengpa. We've been looking forward to this day for a long time because there's been this fantastic research going on, and as part of the CCG, Climate Compatible Growth Program, from our researchers, and particularly in this program research part of the CCG program. And we wanted to really showcase the great research that's been going on. There's lots of papers coming out and in place, so to really just give a chance for our researchers to talk about their work. So thank you firstly to coming along. Thanks to all the speakers and our guest speakers as well.
Thank you, everyone, for coming. Just seconding what you have done. This is a really important day for us because we rarely have this opportunity to showcase the research on critical minerals that's going on in the project, getting feedback and getting an open discussion about the key gaps in knowledge and research questions that as academics we should endeavor to explore. So we really look forward to talking to all of you and to the discussions and the talks that we will have tonight. So welcome.
Thank you. I'm going to get started. So firstly, just a little bit of context around climate compatible growth. This is quite a large project funded by the Foreign Commonwealth Development Office, and it spans about 7 different universities. So we've got UCL, Oxford, Cambridge, Imperial, Strathclyde, Open University, plus KTH in Sweden, and some other organisations. And it's really looking at sustainable energy and transport systems. So that's its basis. I'll come and grab a seat. Anyway, it started off looking at what do sustainable energy and transport systems look like, particularly in the Global South or developing countries or LMICs in those countries. And there's a real focus on building partnership with countries as well. And there's 3 parts of the program. There's the international partnerships, which is really around connecting with the likes of the development banks, international organizations, and where we take kind of some of the tools that have been developed in CCG and really push them out to countries. Is our country partnerships team, which build in-country partnerships. So we're working in 6 different countries at the moment, and we have teams on the ground there, which just helps facilitate this research and co-development of research. And then today, the focus is the program research team. So this is, in each of the universities, there are academics and researchers, I guess, working on some of the gaps in knowledge and the problems that need to be addressed. And so today our focus is this program research and showing off some of that. Why are we focusing on critical minerals? So I said the program's about energy and transport systems. And what we found very quickly is you need, obviously, materials to create new energy and transport systems, and particularly the critical minerals are needed for these new technologies. Our low carbon future, if you were going to net zero or low carbon future, requires shifting away from fossil fuels to extracting energy from wind, solar, and other places. And those technologies are much more material intensive. So you just think about the material in an EV car versus the material in a combustion car, for instance. It requires more materials in these new technologies, obviously less fossil fuels, which is great, but also much more complicated systems. So much more complex electronics. You just think about the types of chemistries and batteries. And some of the materials that are required are these critical minerals to make them work. And these critical minerals are displaced across the world in very specific places. For instance, cobalt being in the DRC, but also in a few other places, but quite challenging geopoliticals around accessing these materials. And also because often these minerals are in less wealthy nations, we have environmental and social risk impacts in those nations where You have wealthy nations wanting products, big mining companies going in. Sometimes the environmental and social impacts are not taken care properly. So that's what we're doing. And just to say, in CCG, we've got two main areas working on critical minerals: the international partnerships, which is taking a platform offering of some research that we did previously, looking at countries, particularly in the Southern Africa region, and analysing the transport and energy infrastructure. We'll hear some of that today as we go along. And then this program research, which is really the research base where we're developing the tools, co-creating data sets, all open source as well for those teams. And the program, this diagram just shows what the program research is like. It's broken into a number of different themes and cross-cutting. And this is the critical minerals cross-cutting theme. But we've got obviously different communities as well within program research. Why are we doing research in this critical mineral space? Well, there are lots and lots of reports coming out on critical minerals, and it's become very, very trendy for countries and organizations to do critical minerals reports. I've splashed up a few here, particularly the UK's critical mineral strategies. But the area of critical minerals as an academic kind of space is not as well developed as some other areas, like, for instance, climate science or financial risk. So I think the rigor that we would expect sometimes in these reports isn't always there. And I think that's a key gap for the academic community, the research community, to really look at getting data. It's complicated. These are vast supply chains, lots of companies, lots of different spaces, lots of different stakeholders interacting. Data is very scarce. And so I think there is an opportunity here for the academic research community, many of you here, to really push forward the methods and the tools and the open source data so we can make better decisions. And so hopefully some of the reports are not just glossy reports, but we get some better evidence into those as well. So I think it's really important. And just to say, the types of questions that we're interested in the program research part of CCG is, how do we define even what critical means? Critical to who? Is it critical just to the wealthy, rich nations who want EVs and solar panels, or is it critical? How do we define what that means? How do we define risk across those supply chains? What does it look like in the future? So which critical minerals will be in hot demand in the future? That depends on what technologies are coming through, what battery technologies, what solar panel, wind turbine technologies. How much of this material will we need? Depends on populations, GDP assumptions. And that whole scenario work, we tend to find in the reports, you just get given a number with no uncertainty on it. So actually working properly, rigorously to find uncertainty about future is really important. What are the key risks to resilience? And this is supply chains. So these supply chains come often from Africa, South America, through China or Asia a lot of the time. And we have really no understanding of the physical mapping of those properly and the risks and resilience issues in those. And so if we want to be able to secure critical minerals for the future, we need to understand how those supply chains work. And what are these ESG, environmental, social, and governance challenges? We're finding, mining companies are often coming externally into these countries, signing up to protocols to look after the environment and social, but often not actually following through. So how do countries ensure that the regulations in place are actually enforced well? And just to say, we've got about 10 plus publications across program research that are either being published or are in review at the moment. So that's all coming through. You'll see hopefully quite a lot of that work today. Policy briefs coming out. We've put 3 dashboards up online. There's some open source models, tools, data sets, just featuring one of the papers that we've got through recently. So that's all from me. That's just a little introduction. Why critical minerals? why is climate compatible growth focusing on this, and a little bit about the program research. And the leader of the program research area, Professor Adam Hawkes, will give a little bit more on that in the second session. So today we've got 4 sessions. They're an hour each, so it's really easy. We've got 3 talks in each session, and then we've got a panel discussion. So we really want you engaging, particularly with these panel discussions. We're not going to have questions after each talk, or maybe just one short one, but we want to really reserve, kind of get into some depth in these discussions in between. So the 4 sessions, one's on critical minerals for the low carbon transport. That's looking what materials will we need. Low carbon transition, what materials will we need in the future. One on mapping supply chains from mines through to markets. One on environmental social impacts, policy and governance. And one on risk assessment and mitigation strategies for the day. So these are the speakers that we've got. It's saying there's 3 speakers each. We've focused this really heavily on the research. So we've asked the teams to talk about the papers that they're working on and talk about the work, etc. And so coming to the first session, ahead of time already, because we're supposed to start at 1:15. So our first session is on critical minerals for low carbon transition. What we're talking about really here is we know we need to move from fossil fuels to these other technologies, and we're trying to understand a little bit how quickly that will happen, what that transition looks like, and therefore what will be the demand in the future for critical minerals. And so this includes things like doing stock models, understanding technologies, how long those technologies are used for, when will those materials be available for recycling, and looking at trying to predict what's the likely demand for these critical minerals in the future. And so our first speaker is Professor Matthew Davies from Swansea University, who's an expert on solar and has done a lot of work in Africa on solar as well. Matthew's not from the Climate Compatible Growth Program. We've brought him in as a guest, really. Just set the scene around these technologies.
Great, thank you very much. Thank you to the organisers. It's a real pleasure to be here today. I'm just going to start my timer so I don't talk too long. So I'm going to talk about quite a lot of things, mainly the drivers for our research and our approach to our research. I'm a chemist by background, and generally I work on next generation solar energy technologies. I'm not going to talk too much about them today, more on the opportunities that I think they bring. And I'm going to talk a little bit about silicon photovoltaics and potentially recovering some waste and critical raw materials from silicon panels. I'm going to start with this diagram that I really like, that I think summarizes our current position. So this is from 1900s into the future, into 2050, and this black line here is the mass of materials that we have extracted from the earth. With that, we have grown our economies, created great advance in standards of living and opportunities for people. So all of that is fantastic. Unfortunately, it's brought this orange line with it, which is carbon emissions into our atmosphere. So now what we need to do into the future is to look how we decouple our economy from the primary consumption of materials. How do we reduce the amount of materials that we mine and use greater sources of secondary materials? That's ultimately the challenge in front of us, and how we become more circular. And if we can do that, we can reduce carbon emissions into our atmosphere and try to mitigate some of the challenges of climate change. Circular economy has become a very important topic, and I'm sure one that you're all now familiar with, but that hasn't actually translated through to any development yet. So last year, we currently extract just over 100 gigatons of materials a year from the earth, and we're down to less than 7% cycled now. This number has reduced year on year for the last 5 years. So even though we're becoming more aware of these issues, we have this contradiction, if you like, of our current needs and how we push forward the green energy transition while becoming more circular. And I think that's a big challenge ahead of us. We know materials demand and materials use is going to increase significantly. As Jonathan mentioned, we need significantly more critical minerals going forward as we transition from a fossil fuel-based economy to a mineral-based economy. So how do we manage some of those things? And this is something that concerns me greatly. So of course, this is the periodic table of elements. You may have seen lots of different types of this diagram, and I'm trying to convey the same thing. All of the elements that are coloured in are essentially critical, and what we've done is we've colour-coded the current recycling rates of these materials, of these elements, and you can see we don't do fantastically well other than elements that have inherent high economic value, like gold, platinum, palladium, things like that. And we start to deploy technologies that have high concentrations, well, they're actually quite low concentrations, or higher requirements of these critical materials. And we do so fairly in isolation. So one of my concerns for the future is to mitigate climate change, we need to deploy technologies very quickly. And we can't end up in a scenario where these technologies that we need to mitigate climate change have to compete for the same critical raw materials. We tend to map technologies forward in isolation, but in reality, we need huge expansion of wind, low energy lighting, battery technologies, and solar PV at the same time. And that brings a high degree of uncertainty. And that's something that we need to manage. Okay. One source of potential critical materials we will have in the future is e-waste. So it's the fastest growing waste stream on the planet. We know we produced a lot of electronic waste. One of the problems is that generally we design technologies in a linear fashion. We design them for a single lifetime, and then we dissipate them into the environment. They essentially go to waste. And if we think about solar in this regard, IRENA did a report back in 2016 that has been discussed quite a lot in the field, but they estimated that there would be 60 million tons of silicon photovoltaic waste by mid-century. To put this into context, this isn't a huge amount of waste compared to other waste streams that we produce as humankind, but it does have a lot of critical materials locked in that technology that we can extract value from, but generally we haven't designed it to do so. So if we were to recover these materials, we could generate up to $15 billion in raw material value. The only thing is we haven't designed it very well to do that, and I'm going to discuss that in just a moment. So this number was a little bit out of date, this 60 million tons. So we wanted to look at an updated forecast of photovoltaic deployment and then recovery from waste, and how much, if we start recycling very efficiently, how much of the supply chain could we replace with secondary materials compared to primary materials and solve some of these problems. So these are two quite complicated graphs, at least in the amount of data that they have. So basically we've mapped two different deployment scenarios, which is called early loss and regular loss. You may be aware of these already, but this basically dictates the lifetime. Not sure how that's happened. The lifetime of the panels. And what we've done here is set a 14 terawatt target, hitting 14 terawatts of installed solar capacity by the mid-century, and then just maintaining 14 terawatts. So not trying to do anything too complicated here. Of course, if we hit 14 terawatts, you could make an argument that we will likely then increase capacity. But these two lines show how much we need to manufacture to just maintain 14 terawatts, given that these panels generally have a lifetime between 20 and 30 years. And then what we've done is mapped the waste arising from the deployment of these technologies, which is on the right-hand side, again, depending on regular loss or early loss, and then when that waste becomes available. And then what we did is something quite simple and probably not very realistic. We looked at the current best lab recycling rates of these materials, so not at an industrial scale, just to see if we do manage to recycle these panels efficiently, how much materials can we get back? So it turns out, because of the way the deployment works, by mid-century, we could only substitute about 10% of the primary material demand. Towards the end of the century, we could substitute between sort of 85 and 95% of the primary demand, just maintaining 14 terawatts. This tells us a little bit about how we have to go about this transition that we face. So we are going to have to rely on primary extraction and mining of critical materials to fuel the green energy transition, at least until the mid-century, when potentially then we get greater waste stocks online to recover critical raw materials. But we have to be prepared for the second half of the century. We can't continue as normal and just react to that problem when we get there. So we need to innovate more efficient recycling processes of this technology to be ready to extract this waste usefully. Bear in mind that solar panels globally, the cheapest thing to do with solar panels still is landfill them. Wherever we don't have regulation in place, generally we see photovoltaic panels will be landfill greater than any other outcome. Okay, so I'll move on there. And this is really important, how we manage this waste. Like I said, the majority ends up in landfill. A great deal of my work is currently looking at potential deployment of next generation solar across the continent of Africa. I work across several countries on the continent, and we see that generally this waste creates huge social and health hazard problems, right? So generally e-waste on the continent, and I am speaking in generalities here, is handled by the informal sector, at great damage to their health, at great damage to the health of the environment. So how do we produce technologies that are inherently more sustainable, that aren't designed for a single lifetime? And certainly, what are the opportunities for next generation technologies that perhaps we can manufacture more locally, democratize energy, and if we do that, we can build skills around remanufacturing and end-of-life treatment, so we avoid some of these problems around hazardous waste at end of life. The problem is, when you think of how we use our critical minerals, generally we dissipate them, they have value, so we use them in small quantities, of course, to try to be efficient. We don't really tell people where they are or what quantities they have in product. So this is where we did some mapping of CRMs across the circuit board. And we've tried to extract some of these CRMs and feed them into the PV manufacturing and things like that. But we have to be better at design. When you think about how we design a photovoltaic panel, it may come up in a second. Generally, we laminate everything together. This makes it very difficult to treat at end of life. Generally, we strip off the aluminium frame, that's easy to recover. The rest is shredded. We recover some of the critical materials, but not a great deal. The rest then is downcycled to really low value materials. We need to keep our critical minerals in much higher standards of material stewardship. And this is where I think there's an opportunity for next generation solar, primarily because we can design them before they're commercial. Because we can design them for circularity, so we can design them so at end of life, we can remanufacture them. When we can't remanufacture, can we reuse components, particularly substrates? So if you think about conductive glass in PV, it accounts for over 70% of the embodied carbon and the cost. If we can reuse the substrates, we can produce a second generation PV panel with an energy payback time of something like 33 days, which is really a low embodied energy technology. Also for next generation solar technologies, we can print them at very low cost in fairly, let's say, dirty environments. So they're quite tolerant to defects. That means quite low capex, low opex. So can we distribute manufacture of these technologies, possibly for the UK? At the moment, we're doing a lot of work across several countries in Africa. We're looking to set up perovskite module manufacturing in Nigeria, and we have a project delivering that. I would also say we design products for a linear fashion, so for a single lifetime. We also don't design products very well for countries across the continent of Africa. We design our technologies for Western use, which is quite pristine. How do we design technologies that are more appropriate for use, that will better serve communities that need them? And I think that's one of the things that we can do through next generation solar. There you go. And as I've said, if we can do this, we can also build skills, and we can build skills to potentially handle waste at end of life in a safe fashion, to deliver social benefit through job creation and things like this. We have a lot of research focus on working with communities that deliver technologies that we think are appropriate and actually wanted by communities for use. This is an example of perovskite manufacturing in a t-shirt printing facility in Mexico, where basically one of my colleagues, Professor Tristan Watson, went there, trained the workforce. We managed to print and make perovskite modules in their environment that worked. This sort of shows the level of CapEx. We're a million miles away from silicon technology and the requirements and costs there. There you go. I'm not going to talk too much about this, but I think one thing that really encourages me about perovskite research, there's lots of flaws and lots of things that we need to overcome, but even at an early stage of development, there has been a lot of research on both recycling and remanufacturing in situ of these technologies, and I think that's a really good advance for the field and a good indicator. Of course, if we're going to talk about distributed manufacturing of perovskite technology across the continent of Africa, then we need to look at supply chains. So this isn't really our forte, but we've just started looking at mapping of supply chains and availability of minerals and refining of those minerals across the continent. Luckily for next generation solar technologies, we don't have a huge CRM usage, but we still need to make sure that if we're going to make technologies locally, that we have the materials available to shorten supply chains as much as possible, to shorten carbon and cost and things like that, and keep as much of the value within the continent as possible. We're really interested in this technology, which I haven't really spoken about, but it's a triple mesoscopic perovskite stack. It's less efficient than some of its cousins, but it doesn't require metallic contacts. It has the longest stability of any perovskite architecture to date. You can just screen print it using low-cost technologies, and it has a lifetime of greater than 2 years in accelerated tests, up to 20 years in the field that we're trying to replicate at the moment. And I think that's my last slide. So I'll just say thank you to the funders, thank you all for your attention, and my research group. And I think I might just have a couple of reports that we've worked on for information if everybody's interested. And yeah, thank you for your attention.
Sam, do you want to come up and get ready? While Sam's getting ready, did anyone have a quick question for me?
So you show that we don't have enough materials to recycle to mid-century, but a lot of the existing solar panels in the world are now considered very low efficiency. So would it be best for our government say to encourage early recycling of the current technology and give some subsidies to install newer technology?
Yes, absolutely. That's part of the early loss scenario, because we are seeing that to some degree, just from an economic point of view. So again, I think where we are trying to learn from that is for next generation technologies, do we really need 25, 30-year lifetimes, where probably after 10 years, they're going to be replaced because of the advance in the background anyway. And that's something we're trying to build into our plans. That is generally what happens at the moment is everything is taken offline and stockpiled until recycling can catch up with extracting some of that value. So I think there is a degree of that happening. And certainly we may see that to a greater effect when silicon perovskite tandems start to take greater share of the market, where then you can make much more energy out of your space.
Great. Thank you. We're going to come back to more questions at the panel discussion. So our next speaker is Dr. Sam Stevenson, who's one of the researchers in our group, who's been looking at stocks of these products in the UK. Over to you, Sam.
Hey guys, it's great to see all of you. Yeah, my name's Dr. Sam Stevenson, and I'm going to be trying to tackle kind of one of the second research questions that John mentioned before, which is how many critical minerals do we need for the low carbon transition? And I'm briefly going to touch on two bits of research I'm doing. One, first at the kind of the UK level, and then secondly, some ongoing work at the global level. Cool. So most countries have committed to getting to net zero, okay? And a lot of them have, over the past kind of 5, 6, 7, 8 years, started to put out plans for how they're going to do that. But the exact mechanism of how that's going to happen still remains very uncertain, still remains very unknown. And it's contingent on a bunch of different factors. It's contingent on technologies that we're going to choose, how many electric vehicles we're going to have, how many solar panels, how many wind turbines, what mixture of solar panels and wind turbines, and how much batteries versus nuclear, and also on a bunch of kind of other less technology things, how much kind of social change are countries willing to put up with, how much kind of policy action a government is willing to push through legislation, okay? But we still want to know, given all this uncertainty, how much critical minerals we're going to need and when we're going to need them. In order to start trying to answer this question, one of the things we've been doing is building a new stock flow model that takes the demand that's given to us in various decarbonisation pathways that a country has produced, and then use that to project when and where those critical mineral pathways, those critical minerals will be required. So the first place we tested this new model that we've been building is in the UK. The UK is a great example for us to start with because there's lots of work that's been done to produce different decarbonisation pathways that we can then test and compare, okay? And here we compare 10 different pathways from 3 different organisations, from the National Energy System Operator. Some of you might know this as the future energy scenarios that used to be produced by the National Grid. That's now been brought in-house by the government into this new group called NESO, which I'll refer to. The second set of pathways is from the Climate Change Committee, and some of you may be familiar with the balanced pathway that the Climate Change Committee has been talking about for several years now. And the third set of scenarios, or the third organisation, is the Centre for Research into Energy Demand Solutions, and they have produced some great pathways looking at how you would get to net zero under a low energy demand future. Okay, and so they're included specifically to talk about what a low energy demand future might look like in the context of critical minerals. And that's the name of the 10 pathways that we look at in this analysis. The first thing we did to compare these pathways and compare these different scenarios is we looked at the total stock in service, that's how many critical minerals are in use in the economy in 2050 relative to today, okay? So this is basically all the critical minerals in use in these different pathways. Each dot is a different pathway. And these are the 15 of the 16 critical minerals that are in the UK critical mineral strategy. I've excluded vanadium from this at this moment in time because vanadium is mainly used in CCS and there's no CCS at the moment, so it really puts out of whack these results. But think about CCS in a separate context. What we find here is that there are these 3 minerals in particular, cobalt, graphite, and lithium, that are really dependent on our choice of pathway, okay? Of all the other ones, silicon in PV or rare earths in wind turbines, actually the relative change in stock and service doesn't change that much between the pathways that you choose, okay? Whereas these 3, cobalt, graphite, and lithium, that are particularly found in the batteries of EVs and grid storage, are really impacted by the choice of pathway that we go down over the next 25 years, or the total stock in service is really impacted. So what we did then is actually try to map out the annual incremental demand for these different pathways or the different organizations over the next 25 years, so between 2025 and 2050. And what we find here is that the key change is actually when the peak of demand is going to be, okay? So the low energy demand scenarios in green really hit this peak demand early and then see quite a sharp drop off. And that's because one of the things the low energy demand requires is bringing all that climate action and decarbonisation action much earlier into the decarbonisation period. Compare that to the National Energy System Operator scenarios, the NESO scenarios that see that peak happen slightly later, and the Climate Change Committee, which is a much smoother period of kind of annual change over our analysis period. But critically, what's important is when we actually plot the cumulative demand, we don't see a significant difference between the different scenarios. And the main reason for this is because while there's lower total embodied stock in the low energy demand scenarios, the fixed lifetime of these different technologies means that you'd actually need to replace them before the analysis period is over. Okay, so if they start coming online in 2030, in 2045, you then need to repeat the stock. So it could be that if you extend the actual analysis period, this picture might change. And I should have said that this is for kind of one of these three minerals we looked at, lithium, but we actually see a very similar picture if we look at all three of the minerals that we kind of highlighted before as being of particular interest. Where you do start to see an interesting change is when we look at different scenarios for what's going to happen to the critical mineral intensity. Okay, so we've taken an existing database and added strip for how many critical minerals you need for an electric vehicle, for a wind turbine, for a solar panel, okay, and made some assessments of how this could change in the future. So the two ME scenarios that you see here, material intensity early and material intensity late, both assume a 20% efficiency improvement of material intensity, or material efficiency, sorry, in critical minerals over the analysis period. And this is roughly in line with the broader kind of material efficiency standards and targets that the UK government has set. The other scenario that we've tested is what I call a technology shift scenario. And this is where you see the current mix of battery technologies in the UK, which is a mix of nickel, manganese, and cobalt batteries and lithium iron phosphate batteries, shift towards 100% lithium iron phosphate, or LFP batteries, in and around the year 2040. And what you see here is a massive reduction in the annual demand for cobalt in the UK as we shift towards LFPs, but offset by an increased demand for graphite, okay? Because they have a higher demand for graphite in those LFP batteries. And so here you can start to see the trade-offs that exist between these different technologies and these different battery kind of chemical compositions that we might want to explore in the future. Because while it's while cobalt might be a particularly difficult thing to manage, and we might want to move away from our cobalt demand, what's this mean if we are trading it off against a higher demand for graphite at the same time? The final piece of work that I just want to briefly touch on is future work that we're trying to extend that out up to the global level. And so here, what we're concerned with is how the global demand for critical minerals change over kind of a similar time period. And here we're using what's called shared socioeconomic pathways to create a kind of range of uncertainty for future demand, depending on kind of what the future looks like. And shared socioeconomic pathways are produced by a bunch of climate scientists for informing the IPCC's annual reports, basically to say what is the future going to look like, and what is kind of any demand or growth, or these different kind of characteristics under that. And so we see different amounts of sustainability or inequality or kind of region integration, or kind of these sorts of different kind of macro trends that then pathways are constructed around these narratives. And what happens when we use these narratives as baselines for critical mineral demand, here again we're looking at lithium, is that you get different annual demands for lithium depending on what type of future you're in. Here we compare some baseline scenarios, so these are not decarbonization scenarios, but what the SSPs kind of like broadly think the future would look like without significant additional climate policy to achieve decarbonization. And this is what happens if you actually start to get to a global kind of net zero or Paris aligned scenario that we've talked about. And so here the constraint is that you kind of limit warming to between 1.5 and 2 degrees by 2100. And what you can see here is that the range of annual demand is much, much greater in a world where decarbonization occurs compared to a world where decarbonization doesn't occur. And so in this future, if we're committed to delivering on decarbonization, committed to delivering the Paris agreements, the type of world in which that happens is really important to thinking about how, when, and where those critical minerals are going to be required. Just to briefly sum up some of this work, we don't know what the future is going to look like, okay? And that's really the driving mechanism, the driving kind of ethos behind this work. There's so much uncertainty over what the future could look like, and it's really in our control to how that will happen, okay? The UK is a good case study for trying to understand what the future could look like with regard to critical minerals, because it has so many different decarbonisation pathways we can compare. And it really does see that final stock in service is for cobalt, lithium, and graphite is impacted by our choice of pathway. But it may not necessarily lead to reduced total consumption due to the need to replace this stock. But what we do find is that shifting from our current battery split to 100% LFP batteries would significantly change our demand for critical minerals in the UK. And finally, under a kind of Paris-aligned decarbonisation scenario world, the type of future that we want to kind of create significantly impacts what our final consumption or final demand for critical minerals would be. And I didn't say it when we were kind of looking at the results, but a highly unequal world would require a significantly greater material consumption in order to deliver decarbonisation in that world. Thank you very much.
Philip, do you want to get ready? Quick question for Sam on the work he's been doing.
Right, thanks, Sam. Can I just ask the final sentence? Why is that? That a more equal world requires more utility?
It's basically because everyone's doing everything individually in this world as well. And so you don't really get this kind of cross-border sharing or this international cooperation that leads to a kind of more equitable distribution, but also allowing for kind of recycling or different things to flow amongst communities that reduce total land life. In this very unequal world, you have sky-high kind of different levels of consumption, but also kind of much greater friction between the communities, which doesn't allow for it to. That makes sense? I can explain to you more detail if you want.
Yeah, it'd be good to look into that, because I think you'd be interested in it, including a lot.
Great, thanks, Sam. So our final speaker in this session is Philip Mitchell, who's another research associate in the group. Over to you, Philip.
Okay, hello everybody. I'm a postdoc here in working with Andre and John, and today I'm going to be focusing in a little bit more on lithium and the security of the lithium supply in the UK. So our motivation, sort of our implicit goal, sometimes a little bit more explicitly, we want to maintain UK living standards and population, and we want to reduce our emissions at the same time. This is going to require quite a few different critical minerals from the presentations that we've seen earlier today. I'm going to be focusing on lithium, which is main uses for transition involve both transport and grid scale energy storage. So, but lithium is already being used for multiple other purposes in the economy. So we want to sort of take a step back, look at lithium use in other products, our cell phones, our laptops, lubricants, etc., and what the magnitude of that is, how much lithium is required for renewable energy systems. And because we don't have any really commercial economic supply of reserves of lithium in the United Kingdom, we have to look at supply constraints. Even current day extraction of lithium is leading to incredible environmental damage in certain areas. And then there's a lot of supply chain complexity involved in both the fabrication of lithium containing products. And so we want to sort of take all that and try to model future requirements and the circularity of that. So if we move to the next slide, we'll begin with other uses of lithium. And if I were to ask you all, what is lithium used for? Most of you would say probably batteries. And that's 80%, 87% or so of our usage for this. So this includes laptops, cell phones, in addition to the renewable energy related aspects, grid storage, electrical transport, but also, I mean, a million different other things, e-cigarettes, lawnmowers, even chainsaws, electric chainsaws, etc. It's also used in a number of other things that don't really immediately come to mind. Ceramics and glass, in particular the glass on, say, your stovetop in your house. It's a key ingredient in, say, approximately half or so of lubricant production. As an additive in some metals, in aerospace, pharmaceuticals, lithium is important for the treatment of bipolar disorder, desiccants, and cement treatments. So we want to get a handle of what are the magnitudes of these flows within the United Kingdom, and to do that, we turn to trade data. And here I show the imports and exports of lithium carbonate within the UK. You can see there's slightly more lithium imports. This is mainly going to one particular company that does a lot of both upgrading of lithium carbonate to battery grade lithium carbonate and produces a lot of these other sort of products, desiccants, lithium bromides, etc. What are the magnitudes of the requirements for energy transition? And this is something where here I've shown several of the scenarios that Sam introduced to you earlier. There's a lot of uncertainty. In addition to these scenarios, there's other academic studies that have orders of magnitude greater lithium requirements. So this is an area that we really have to pin down quite a bit more. So I will be introducing today a stock flow model. A stock flow model, very simple. We have all of the lithium embodied in our current stocks of lithium in my cell phone, in our laptops, et cetera, in our electric cars, in our grid batteries. And in order to maintain this demand, there's a certain amount of new products that we have to manufacture and add to the stock each year. And then they'll reach end of life, and we're going to be producing waste products. Now, if you zoom out to the UK economy as a whole, that module I just told you about is here in the use phase. And this boundary is the UK economy. There's a certain amount of lithium that's going to be produced by mines, really marginal, if nothing, from UK mines. There's lithium that's going to be brought in from outside and embodied products. This is our electric cars, etc. Then the products reach end of life. And then there's a complicated process where we have to both collect them, sort them, and then have the recycling facilities available if we want to achieve this circularity. Now, this is a very simplified model, and lithium in particular is complex enough in that there's a lot of intermediate products and manufacturing steps within lithium. So we have to complicate this model slightly. And to do so, we take our in-use lifetime model, which takes into consideration the lifetime of each product and which we can adjust the parameters of. So maybe policymakers want to mandate certain lifetime requirements, say for electric cars. Once we calculate the amount of lithium that's needed each time step, we can conduct an optimization based on the manufacturing capacity of different products. This could include cathodes, upgrading to battery grade lithium, other lubricant production, etc. And when we do so, I'll start with the right-hand side. So in use stock, we specify, and here I've just pulled out grid batteries and electric vehicles. We specify at each time point how many electric vehicles we want, how much grid batteries we want, how much lubricant production we want. Based on the lifetimes that we specify in the model, then we get how much we need as an input and how much we're producing as output. And the goal here is, because we don't have lithium readily available in the UK, is to incorporate some sort of circularity. And reduce our import requirements. So the way this second phase works is we specify what domestic manufacturing capacity we're going to have for each aspect of the supply chain. And so here, for example, I've included, well, we can upgrade a certain amount of battery grade lithium carbonate, and there's a certain level of battery manufacturing capability that already exists in the United Kingdom for electric cars, and there's some that is projected to be added to that in the near future. Then we do an optimization to maximize the amount of domestic production and supply chain we can get. And that gives us the amount of imports and the amount of exports that we can utilize throughout the supply chain. And some brief sort of overall conclusions for this. While lithium is critical to these many sectors, I mentioned pharmaceuticals, lubricants, etc., the magnitude of the requirements in these sectors are dwarfed really by renewable energy storage and electric cars. The actual requirements for these sectors, these key sectors, vary widely. If we look at the magnitudes that are projected for this, and say there's 20 million tons of lithium carbonate reserves, and we say that the UK is maybe 0.8% of the world population. This exceeds sort of our equitable share of lithium. So that's another thing that we need to consider. The lack of lithium reserves is the key point. Necessitates some level of circularity. This requires industrial policy, planning. We have to make sure that if you're someone who's going to be developing and investing in, say, recycling capacity, you need to ensure that you're going to have a steady inflow and stream of waste products. And then if you're manufacturing within the UK, you need to make sure that the waste products that are produced are compatible inputs to your supply stream. So this requires coordination across sectors and of the economy. And that's really the goal of this model. As a planning resource, get everybody in the room, figure out what kind of lithium flows we're going to have available. So that's our physical I/O table and stock flow. Just to wrap up, we're preparing a paper on this, and along the way we've produced some software that I think can be that'll be quite useful for perhaps others in this room, both to analyze trade by HS code and this stock model that I've mentioned today, which is generalized across not just lithium, but you could apply it to copper or any other metal, and to different countries. So your boundaries could be the United Kingdom, but it could just as well be Zambia. So that's what I have.
Thank you. I'm going to ask all the other two speakers to come back up, if that's possible. So we've got 20 minutes. So each of these 1 hour sessions, we're going to have this discussion at the end. So be thinking of questions that you want to ask the panelists. That can be individual questions or more general, all of them. So my first question was really, we see in these critical mineral reports, which I'm sure you've read lots of them, very specific future predictions of, lithium will be 15 times as much, or, cobalt will need to be X. What we're seeing in all three presentations in there is there's a lot of variability, depending on what future we decide and how we go. But how do we manage this this need sometimes in more, report writing to be a bit more simple and clear versus, producing lots of scenarios, which gives us a big range, which then gets very uncertain, very complicated. How do we kind of manage this in a kind of a communication way? So anyone's welcome to talk on that. Matthew, start.
I think very carefully. One of the problems is, if we look historically at things like the IPCC reports on climate change, that the use of language there in being balanced and scientifically accurate allowed leeway for a whole wave of sort of climate skepticism, if you like. So in sort of projecting future demand of materials, I think we also have to be careful, because people can downplay the importance, and that's where I would worry about things. I would say that those headline figures we need to take, of course, with a pinch of salt, and we understand how variable all of the deployment scenarios are. And of course, they depend on so many different things, even things like learning curves, right? How we can use less of those materials. I think one thing we should bear in mind is actually, whenever we've had significant restrictions on particular critical minerals, we've actually done okay at innovating around those and replacing them when they're not central to a particular technology, if that makes sense. Cobalt is a good example, where we managed to look at other materials and substitute out cobalt. So I think we have to be careful with who the reports are for and what the aim of the report is ultimately. What are we looking to achieve from that? I like doing lots of scenario planning when we try to do these things, and it does end up with a very large range of numbers. Scientifically, I think that's fine. Maybe for reports, I understand why they want, sort of particular numbers, but I think we can do that better, of course. Sorry, I'll leave you.
Sam or
No, that was great. I think it's very kind of hard to get away from that appeal by kind of people that write headlines or kind of to make convincing messages just to give a single number. But I think as well, one thing we can do more of is specify the kind of the future that we are talking about when we give a number, to kind of put it in context. And maybe it's not giving an uncertainty around it as we might like in a paper, but you can say, in a future where we don't materially change our living conditions, this is the sort of thing we're looking at. Or in a future where we're much more collaborative or equal, this is the sort of number we're looking at. And so I think that can provide a nice middle ground between giving a kind of a single number that people can kind of understand with and deal with, but also giving the context rather than kind of the uncertainty to what we're talking about or what that would mean for kind of the rest of the world or the economy and that sort of thing, and allow people to kind of think, all right, well, do I want that or do I not want that, or how does that compare against different numbers? So I think giving that context can be really important, in addition to uncertainty or just kind of numerous scenarios that people can't get their head around.
And I would add to that, I think it's very important to understand why we're trying to make these scenarios in the first place. And depending on what we want to get out of these exercises, we might want to make different assumptions. You know, there's a trillion different scenarios that the pathways that could potentially take. But if our interest is, say, purely on will demand meet supply constraints, maybe we can look at sort of the extreme scenarios and on either side and see if those to at least sort of narrow down the scope of what we might need. So yeah, I think creating scenarios for the sake of creating scenarios is maybe not the best, but if we have specific reasons and we're developing scenarios with those assumptions in mind to get particular results, I think that would be helpful.
Just one thing I think we can do significantly better is consider the carbon cost of all of these scenarios as well, because of course we can do things, and you already hear talk of mining the seabed, mining tailings, the urban mines. We can do all of that and extract materials. What is the carbon cost of doing that, and how does it affect our carbon budget? That should be the sort of baseline of how we make decisions, I guess.
That's actually, I think that's something it's really missing in this whole discussion, is the linkage between the mining, manufacturing, et cetera, of all these critical metals, and then the energy requirements. And right now, a lot of that is fossil fuel requirements, and looking at fossil fuel availability then too also filters into all of these different critical metal discussions.
It's interesting. And I think on the circularity and recycling, it was nice seeing that coming through in your analysis, Matthew, where you want to make sure that you're not recycling and using 10 times as much energy to recycle as what you would to make it in the first place. And being very careful not to downgrade. Wondering if there's an audience question. Yeah.
I was just going to add to that point, if that's all right. I think it's a really, really important question. Shall I quickly introduce myself?
Yeah, that's fine.
Maybe, when others come in, it'd be really helpful to quickly introduce yourself. I don't know most of the people in the room. So Lily Ryan Collins, I'm from the Foreign Commonwealth and Development Office, and I oversee CCG's critical minerals work stream. I'm also trying to ensure that CCG and other FCDO-funded research programs such as Transforming Energy Access are joined up on the critical minerals work as well. So yeah, great to be here today. It's a really important question, and one thing I wanted to say was, so policymakers always want simple answers, simple figures, right? Maybe not want the kind of need, cabinet ministers don't have time to read academic papers; they just don't. And so that we'll end up in a situation where there's certain reports or figures that have come to be seen as gospel, right? So, okay, we won't name any names, but this report says this, so that's the figure we're going with. So I think if your work reveals a different story, that's really important to be able to challenge that, and so that the decision makers, the people in those positions of power, have a kind of variety of different options, or not options so much, but that they understand that there are different ideas and different scenarios. Different researchers have got different answers to this. That's a really important thing for policymakers to understand. So yeah, it's just an add-on point. I don't know if this question, I'm not a modeler, but I know that robust decision making is used in the energy space in CCG a lot. I don't know if that's something that could help with this, or is it just the scenario is the number of scenarios you have to run for that just too much for the models that you guys are using?
I can talk from a solar perspective. I think you probably give better answers than me. But the IRENA report that I mentioned about the waste arriving from PV, it was good to see that actually when you put these things out there, the nature of the scientific body is that everybody analyzes it. Some people tear it apart, and then there's weakness in some things that can be improved. But largely what we saw post that report in 2016 is PV deployment outstripped projections significantly. And then I spoke about 14 terawatts, and this is one of the challenges we have. 14 terawatts is the World Energy Transition Outlook target for mid-century. Some people have predicted over 100 terawatts from solar. So, I mean, we have a factor of 10 even in our projections, right? And so it becomes really hard then to make those predictions. And I think that's one of the issues ahead of us. Wind and solar are dominating. And how long will that continue, and how much will they outstrip demand? And it depends on economics and all of the other things. But I think that makes it really difficult, actually.
And I was going to think, I think a really important thing is that although, you know, we challenge numbers, we're not quibbling about the little things and being academic. Because I think, you know, what all three speakers this morning showing is because we're going to need a lot of critical minerals. I mean, whether it's a lot or a little bit less a lot, it's still a lot. And interestingly, what you were showing, Sham, of the different deployment scenarios, that the cumulative's about the same, which means we need about the same amount of materials in total, which is really revealing. The energy scenario doesn't fit as much. I think, did you have a question? No, move. I had another question. So,
as you said, with Sam's model and across the scenarios, that the cumulative model was quite similar. But then in Philip's presentation, he said that there was a lot of variation in the requirement for storage of lithium. It could just be a deficiency in my understanding, but would you be able to kind of reconcile those two?
Well, not just in the storage, but storage is then also, you have an order of magnitude more than in electrical car batteries too. So some of it can get masked by, so you have uncertainty in sort of each of these components. And maybe the uncertainty in the electrical car projections, for example, are less than grid storage.
I think as well, part of it is the kind of time frame that we're looking over. So we've taken a very fixed kind of up to 2050 because that's when decarbonisation targets all seek to meet. But if you project it out until 2100 in the UK, you might start to see significant variations in cumulative demand because we saw that difference in kind of total stock and service right at the start, which would then kind of, I think, be more in line with the differences that Philip showed. And also, if we started to test things around kind of like vehicle lifetimes and technology lifetimes and how that impacted the cumulative demand, which is kind of one of the values of using and building this stock flow model, which is something we can do in the future, you then might start to see these kind of differences come in. But I think at the moment, it's just that kind of fixed time frame that hides a lot of the kind of interesting nuance that we can continue to explore.
And I would add to that too, that regardless of these scenarios, there are certain issues that we're going to have to tackle, whether that's how do we handle, I mean, demand, I think in a lot of these scenarios outstrip supply. That might be maybe farther in the future, but at some point we have that issue. And even the supply that we have right now is being, sort of the industrial scale of it is already causing a huge amount of environmental problems. So regardless of the scenario, those are issues that we're going to have to discuss and work towards. And I think something that FCDO in particular is quite interested in, being involved in a lot of these developing countries. How can we make sure that it's just not, you know, the UK extracting all of these materials and then leaving mine tailings and wetland destruction, etc. In these countries. So
I had a quick question. This is only have to be one word answer, which is which critical mineral are you most concerned about? Or material, not even critical, maybe. What is there one that you think we should worry about?
So for me, high purity quartz for silicon, just because you can't substitute. While it's not currently critical, I think.
Well, yeah, it's not on any critical
No,
list.
I know.
That's why I'm asking the question. Interesting. Yeah.
I would say oil. So that might be be a very different answer. But I think with sort of being in the midst of peak oil supply, that's going to have repercussions on the affordability of the mining across the mining sector. So I think figuring out how we can incorporate and look at both energy and energy requirements for the mining of the critical metals and how much we can electrify those processes is incredibly important.
That's fine. You need to explain oil.
Yeah, this wasn't in what I presented, but I think rare earths, and particularly because the rare earth kind of category at the moment conflates a huge amount of different minerals that are not used for the same thing. And so when we conflate them, you get rare earths that are used in internal combustion engines aligned with rare earths that are used in wind turbines that the analysis says can be kind of recycled or interchanged. And that's really not what we're seeing. So more detail in rare earths, I think, is needed.
Yeah, and I think just to say that CCG is doing quite a lot of work on moving away from diesel in mining to maybe solar panels. So that's really interesting. And on the rare earth one, but we'll hear about that in the supply chains. But in the supply chains, rare earths is the one where one country particularly dominates both the mining and the processing of rare earths. Whereas some of the other materials, it's a bit of a mixed bag. Question? Well, I've got lots more, but I have.
Thanks, John. Thank you all. I'm Laura Blizzard. I work for the Foreign Commonwealth Development Office with Lily, but in a different department, in the Economic Development Department. A couple of questions, one around circular approaches and one around the printed solar panels. On the latter, you mentioned that you looked at particular case studies. Is that a very innovative space that that is requiring a bit more kind of research and practical application before investment can come into that space, or is there particular reasons why that hasn't been scaled up more? It'd be really good to hear from you on that. And the second one on circularity approaches, it seems to me from both the kind of demand side on kind of lithium and next gen solar, etc., that thinking about eco-design and circularity is going to be far more beneficial for us if we do it together with others. You mentioned about broader cooperation and working with others and thinking about agreeing certain standardization around design. It doesn't appear that there's much of a forum at the moment for that. And certainly something we as FCO are considering in some of our international work. But just wanted a reflections on if there are existing dialogues or advances in conversations across border that might help with that. Thanks.
I'll try to remember. Yeah. So in terms of manufacturing perovskite solar, I think we always say it's on the cusp of commercialization. We've been saying that for many years. Oxford PV are producing silicon perovskite tandems, but they will, in my opinion, not be fantastically useful for transforming energy access. We're looking at single junction perovskites, low capex, distributed manufacturing. We think the technology is nearly there. Through one of our funded projects, we hope to demonstrate module manufacturing in the coming years, and from there really cement the business case for investing in manufacturing across the continent of Africa. So, and I'm happy to discuss that further. In terms of circularity, a couple of things. Eco-design and design for circular economy are two slightly different things. Eco-design looks to minimize the environmental footprint of a product. Design for circular economy looks to design it in such a way that we can recover and reuse and maintain materials in the tightest loop of the circular economy. One of the key things in overall design for circular economy, of course, is that industrial symbiosis. And that's something that needs an enormous amount of work, particularly around waste legislation. So industrial symbiosis is where we take waste for one industry and use it as feedstocks in another industry. We've been doing quite a lot of work with various professional bodies on waste. And we've heard some shocking examples from the UK where waste can't be reused. One striking example is where material, a road was being relayed essentially, and the rocks that were dug up from the road couldn't be put back into the road because they were classified as waste. I mean, that's just ludicrous. We need to think about legislation that enables circularity, and waste is a key, waste regulation is a key thing there. But obviously we have to maintain protection of the environment and people and things like that as well around that.
I was going to say, do you think that if we went for lower technology manufacturing, which you're promoting to allow countries in Africa to do their own manufacturing, that also enables the circularity as well, because the technology is more simpler, perhaps, to recycle?
Certainly in terms of capital investment. So I think this is something that's somewhat unique, but we might think about it in design of all next generation technologies. Perovskites in particular are very tolerant to defects, so we can make them in fairly dusty environments. Silicon has to be super pure, so you have to invest in your manufacturing. But I think what transforming energy access needs is a holistic approach. Currently, again, sweeping generalities, but what we see is the importation of lower quality silicon wafers that tend to fail early, that create waste. There's problems with EPR and taking them back to where they might be bought and things like that. So they generally end up in waste, and then they're generally not treated very well at end of life. So that's where I think distributed manufacturing coupled with skills development for end of life treatment and design for circular economy starts to answer several of those problems at the same time.
It's really interesting. Maybe it's a strategy. So, I think we're almost out. One more, last one.
It was more just a comment on Matteo from UC Davis. The comment of, yes, we need lots of circularity and we need to design regulations around this. One of the bodies that's currently leading on this is the European Commission, which I would urge the UK still to be involved with incentivizing some of those regulations. And yes, we need sort of circular approaches, but they don't have to necessarily be national at UK level. For example, when vehicles ends their life here in the UK, they then go to other countries. And so that can be sort of within Europe, most cars will end their life within Europe. So yeah, regional at least, if not more global.
And we were seeing that regional scenario. I'm going to stop it there because I think that clock's actually a bit slow as well. We've got 15 minutes for a cup of tea and a break. Chat to each other. We're back here at 11:30. Next session. So